You are given a line graph where each vertex I is connected to its left neighbor by a white edge that you see on the screen. So there will be a total of n minus 1 white edges. Then on top of this line graph, you have some additional orange edges that spawn in any direction and can go from any vertex to the other vertex. For example, one possible edge is from 1 to 3. Other possible edge in the opposite direction is from 6 to 4. So your goal is that given this particular kind of graph, find out in how many ways can you delete some of these orange edges. Note that you are not allowed to touch any of the white edges. These are fixed so that it remains at least a line graph. Your goal is to find out in how many ways can you delete some of the orange edges such that the resulting graph is strongly connected. And what do I mean by strongly connected? It means that pick any two vertices in the entire set of nodes that you have. Then there should be a path from A to B as well as from B to A. Not necessarily a direct edge between them, but there should be a path between these two uh, nodes. So that is what strongly connected means. So you are given this problem and you need to come up with a strategy to find out the number of ways you can delete some of these orange edges such that the resulting graph is still strongly connected. Now, given such a problem, how do you even start thinking about it? Like, what's the first step? So in this video, we'll talk about various brainstorming ideas. We'll brainstorm some ideas related to this problem. We will not focus much on the implementation or the optimization. Our goal is to just understand how to even start tackling this problem. And you might be scared just by looking at keywords like strongly connected and graphs. But the thing is, if you do not brainstorm these kind of problems, then you will never improve on these kind of problems. So eventually you have to take that leap of faith and attempt the problems that are out of your comfort zone. Even if you are not implementing them, at least try to learn how to start thinking about the problems in the correct direction. So now let's jump into the solution. So before we start with any complex orange edges that we have, let's first discuss the case of the simplest line graph that we have where no orange edge is available at this point of time. So let me take this graph. Now you will see that this particular line graph is very close to being strongly connected. Why? Because any vertex can reach any vertex but only in one direction. For example, if you pick a particular vertex 5, okay, it can reach vertex 4 and vertex 3 and vertex 2 and vertex 1 and so on. Similarly, vertex 7 can reach all the vertices towards its left. This is exactly what a line graph means. So this means that everything, all your roads are leading to the vertex 1, right? Everyone can reach 1. This is one fact that you can state, like all the vertices can reach 1. Now, if the graph has to be strongly connected, then the vertex 1 should be able to reach all the vertices that are possible, right? So vertex 1 should be able to reach vertex 2 as well as vertex 3 as well as vertex 4 as well as vertex 5 as well as vertex 6 as well as vertex 7. But now notice some interesting properties about the lines, this curved arrows that I have drawn. Since you already have a path from any of the vertex to 1, then you can notice that it is not necessary that vertex 1 has a direct connection with vertex 2 or vertex 3 or vertex 4 or all the vertices, right? A direct connection is not necessary because you can have some indirect connection as well. For example, if you just add one edge, can you make the graph strongly connected? So if I were to ask you to add just one particular edge, so you can see that you can still make the graph strongly connected if you start from this vertex 1 and add the edge to the highest possible, which is 7. Why? Because we saw that everybody can reach vertex 1, right? And if one can reach the maximum distance, then this graph is already strongly connected, right? Strongly connected. So this is, you can see that this is the simplest example wherein adding just a single edge led to the graph being strongly connected, because it is forming a cycle, and everything in a cycle, they are reachable from each other. And how do you reach, like let's say, how do you reach 6 from 3? It's simple. You start from 3 and you know that there is always a way to reach 1, and from 1 you know that there is always a way to reach the last vertex, and you know that from the last vertex there is always a way to reach the all the previous vertices. So you come back over here. Why is any of this working? Because this is a line graph. So one very crucial observation that we have made is that from 1, if you can reach 7 either directly or indirectly, then your answer is valid. And this is a necessary condition, right? But you can see that this is also a sufficient condition as well. Like reaching 7 either directly or indirectly is a sufficient condition, but also an unnecessary condition, because if you're not able to reach 7 from 1, then 1 does not follow the condition of strongly connected. So that is why you can say that necessary or sufficient, necessary as well as sufficient condition. Let me write that down. Necessary and sufficient condition is one should be able to reach n directly or indirectly. And note that indirect connection is also possible. For example, you can go from 1 to 4 and then go from 4 to 7, and this graph is still strongly connected. Why? Because your eventual goal was making a path from 1 to 7, basically closing that cycle. You have to create a cycle, otherwise it will not work, right? Or, so what are the possible paths can look like? Okay, let's explore that. So let me pick up this graph again. Now you see that our only condition to make the graph strongly connected is you connect one to all the vertices, but you don't have to connect it to all the vertices. You just have to ensure that it is connected to the highest vertices. Now, how can we do that? One possible way is from going directly 1 to 7. In one step, you are done. The other way is going in hops 1 to 3, and then 3 to 5, and then 5 to 7. Now, what is the last possible way that we are missing? The last possible way is that these hops do not need to be consecutives. Another way to still reach 7 is to make bigger jumps. Like let's say you go from 1 to 4. Okay, assume that there is a edge from 1 to 4. So one will be able to reach till 4. But then if the second edge is from 2 to 5, and the third edge is from 5 to 7, then also the graph is strongly connected. Why? Because remember the property that for a line graph, I can reach any vertex that is less than I. That is the definition of line graph. So it means that when you are making that hop, when you are starting from 1 and you have reached point 4, then in order to make the next jump, you don't have to necessarily start at point 4. If you want to go back, there is a way, because this is a line graph. So if you want to follow a path till 7, I can show you how that path looks like. So you start from 1, you go till 4, and then you come back till 2, and then you take a jump till 5, and then from 5 you go till 7. So this means that you just need to have a series of hops that can lead you from 1 to 7, and these series of hops, they can either look like just one single hop, or contiguous set of hops, or a set of hops that looks like this. You make the first jump over here, but the second jump has to start from the left hand side and lead to something bigger, and then the third jump has to start on the left hand side of this point, and then it has to lead to something bigger, and eventually you should reach the last element. So these are some of the crucial observations we have made, and in fact majority of this video will be about observation only, not about some specific data structures that you can apply to optimize the solution of this problem, because what we are focusing on is improving our thinking skills, and you can do that by looking at a completely random problem and then making some observation or improving your deduction skills based on that. Okay, now let's talk about the solution. So far we have concluded that you only need to keep track of whether you can reach certain index by a series of jumps starting from index 1. Now notice another observation, that when you start from 1 and when you go to index 4, it is also possible to go to index from 1, it is also possible to go to index 2, right? Because we said that this biggest jump will create strongly connected. So why is it possible to go from 1 to 2? Because you can go from 1 to 4 and then you can come back, right? So this is the most important property of the line graph, that you are allowed to come back. So if you are able to make the jump from 1 to x, then you can make the jump from, or you can locate a path from 1 to any number which is less than x. Does that make sense? You should be able to locate that path. And how can you do that? You make that jump and then you come back, because it is a line graph. So now if I ask you to compute the number of ways to delete the orange edges such that the resulting graph is still connected component, such that the resulting graph is strongly connected. So you can notice that you can take each edge independently. So there are two choices for each edge. You can either keep it in your final graph, or you can leave it. You can keep that edge or you can leave that edge. So if there are a total of m edges, m orange edges, then the time complexity would be 2 to the power n. Sorry, not the time complexity, the total number of choices to select a subset of the orange edges would be 2 to the power m. Now the problem is asking you to delete a subset of the edges, but you can notice that when you were learning about sets and subsets, or more specifically when you were learning about NCR, you must remember that NCR is equal to n minus NC n minus R. Why is that true? Because to select R integers from n integers, there is NCR choices, but the remaining, instead of selecting R for your final set, you could have as well selected n minus R that you want to discard. So you can apply the same philosophy over here, that instead of selecting the edges that you want to keep in your final set, you can instead start with a clean slate, and the clean slate is what we have been discussing so far, that is starting with a line graph, and then you can add a subset of edges that you want to keep, right? Instead of starting with this complex state, with all these orange edges. You can start with a clean slate and then you can decide which subset of the orange edges you can keep. So hope you can see why the both the problems are equivalent. That is, all possible subset deletion, all possible subset deletion is equal to is equivalent to all possible subset addition. That is, you start with just a line graph and then start incrementally adding edges to that graph. So all possible subset addition. So now that we have simplified the problem, let's look at what happens when you incrementally add one orange edge to this starting graph. So if you have this starting graph, let's look at the first edge that you might add. Suppose it is from this to this, from 3 to 5. So for the first edge, you have two choices. You can either keep this line graph as it is, or you have two choices. You can either keep the line graph as it is, or you can keep the line graph and then add an edge that looks like this. Now, when you introduce the second edge, suppose the second edge is from 2 to 6, then in both of these choices that you have split, you can further split into two choices. You either keep the current incoming edge from 2 to 6, or you do not keep it. So if you do not keep it, you will still end up with this simple line graph. Or if you decide to keep this edge, then you will end up with this structure, this line graph and then this particular edge. And in this variation where you decided to keep the first edge, here also you can make the same choice again. That is, you decide to not keep this single edge, newly added edge, then you will retain this graph. You will have this graph with just this upper edge. And if you decided to keep this newly added edge, then you will have this line graph with upper edge and the lower edge added. So as you can see, when you start incrementally adding edges, at each point, you have two choices for the edge. So that's why your number of graphs that you have to keep maintaining. So the number of graphs that are blue in color that you have to maintain is 2. But the number of graphs that are green in color that you have to maintain is 4. And then when the next edge arrives, this will also split into two further choices. This will also split into two further choices, etc. So that's why when the nth edge arrives, you have to maintain to the power n states. Basically, those are graphs. So of course it is not feasible to store this many graph when you are incrementally adding edges. So can we simplify that further? That is, do we really need to know so much details about the graph, or can we do with some limited set of information and then we can group the graphs together that share some particular characteristic? So notice that if you have something like, if you have a graph where an edge goes from 2 to 4 and an edge goes from 4 to 6, so this creates a connected component where 2, 3, 4, 5, 6, they are part of that same connected component. But if you had another graph where the edges went like this, 2 to 3, 3 to 4, 4 to 5, 5 to 6, like this order, then you will notice that these two graphs are essentially equivalent because they are forming connected component with the same set of elements. So you don't have to maintain these two as a separate graph. Another example, like if you had another graph with direct connection from 2 to 6, then all the three colored graphs that you see, like with the red edges and with the green edges and with the white edges, all three of them are equivalent. So all you care about is how many elements are part of one single connected component. So if you can just maintain that set, then it might be easier to handle, and you can put all of these graphs into that equivalent set. But if you think about it, even that can get pretty big very quickly, right? Because in the first iteration, you might have something like, you might have an edge from 2 to 3, but then in the second edge you might have the edge from 4 to 5, so that will also grow very quickly. So we have to think whether we can simplify it down even further. Like, do we really need to store all the strongly connected components that are being created? Like, do we need to classify the graphs according to the number of strongly connected components? If you remember our discussions earlier, second. Yeah. So if you remember our discussions from earlier, we said that the entire algorithm is decided by how well connected the vertex 1 is. So if we had proved that that was the necessary as well as a sufficient condition. So if we can somehow prove, or if we can somehow keep track of how much progress vertex 1 has made towards being strongly connected, then we should be able to solve the problem, right? So for example, if in the first edge vertex 1 has a connection from 1 to 3, so you know that if you can reach 1 to 3, you can, if you can reach the third endpoint, you can also reach the second endpoint. So no need to maintain that information. If you just maintain what is the max vertex that you can reach from vertex 1, max vertex that you can reach from 1. So if you, so there are n possible choices of this max vertex, so then you will have n different equivalence classes. Like you can, all the graphs in which you can only reach from 1 to 1, you put them into this box. All the graphs in which you can only reach up till 2, you put them into this box, and so on. And then you keep a count of how many elements you have put into each box. Okay. And then when you add a new edge, you can then decide that whether that, when, if you are adding the edge from let's say 3 to 5, then you can decide whether this edge is extending the maximum possible vertex that you are already capable of reaching. So you can maintain this set, but one major flaw with this issue, with this approach, is that suppose your starting set is, suppose your starting edge that you introduce, the first orange edge, is from 3 to 6. So in that case, what is the nature of this graph? Like, which equivalence class does it fall into? Is it the equivalence class where you can reach vertex 1 or 2 or 3 or 4 and so on? So you will see that by definition in this graph you can only reach up till vertex 1. So you will store this graph in this block, right? You can only reach up till vertex 1. But then in the next two rounds, suppose if I add something like, if I add the edge which goes from 1 to 3, and then from 6 to 7, then you will notice that when you added 1 to 3, you forgot the information that 3 to 6 was indeed reachable, right? Because you did not store that information, because you are only focusing on the nodes that are reachable from the first node. So that's why if you just track what is the maximum vertex that you can reach from the first element, then it will be difficult to handle the cases where it is not possible to reach any element, but this edge might contribute in future. So to handle this case, we can instead apply a trick where we process the edges in sorted order of their endpoints, their left endpoint. So if we process edges in sorted order of left endpoint. So we have made two modifications. One is we took the liberty of we took the liberty of uh, adding the orange edges one by one instead of deleting them, and we proved that it is equivalent. And the other liberty that we are taking is, instead of processing the edges in a random fashion, we are just processing them in a sorted order, right? And you can see that the answer will not change, right? Because the answer does not care in what order you process the edges, as long as you compute the correct answer. So now let's look at the final algorithm on how you can maintain the number of strongly connected components, or the number of graphs that are very close to reaching the strongly connected criteria, while iterating through the edges from left to right. And we already saw that we'll create equivalence classes where we will classify the graphs into one of n categories. It will either fall in category 1 or category 2 or category 3 and so on, or it will fall in category n. So there can be only n different kinds of graph. So you can see that since we added this condition that there can only be n different kinds of graph, and every graph can necessarily fit into exactly one box, so that disjoint thing has to be true. Then you will see that the number of choices at each edge addition, that will not explode, because the number of graph type remains n at each stage. Only their counts will change, right? Only their counts will change. So now first you will process all the edges that start at 1, and then when they start at 1, some edge will lead to from 1 to 3, some edge might lead to 1 to 4, some edge might lead to 1 to 5, someone might lead to 1 to 6. So in each of these cases, whatever graph you are forming, right, like if the edge is leading from 1 to 3, we are maintaining the max vertex that we can reach from 1. So you update the count, like you do count plus 1 for these graphs that you are maintaining. Now what happens when you process the second element, or when you process the third element? So in general, assume that you are at index 4. So this means that you have already processed all the graphs where the starting edges are 1, 2 and 3, because you are processing them in sorted order. And assume that you want to figure out how to update the number of graphs, right? You have distributed them into different classes, and when you add a new entry, how many new graphs will be added to each of these entries? So now suppose we are dealing with a case where the where the edge that you are adding is, let's say, from 4 to 6. Okay. Now, and you iterate over all of these disjoint classes for the graphs, and for each element, here, like if you are considering the max reach as r, right, then it means that in this, like if this is the box corresponding to r, then this means that count, like whatever the count that this denote, like this is the number of graphs in which it is already possible to reach the value r from 1. And if it is possible to reach the value r, then it means that it is also possible to reach all the values that are less than or equal to r. So the only modifications that can happen is, assume that this is 1, and assume that from 1 you are updating the value of the number of graphs that can reach point r. When you introduce a new edge, suppose that new edge, so that new edge, it can be of three different types. It can either be a backward edge, so assume that it is a backward edge, that is, it starts from here and then goes in the opposite direction. So you can notice that adding a backward edge doesn't really increase the reachability of vertices from the vertex 1, because all the vertex are already reachable from already reachable in the decreasing order in one path, right? So even if you add a shortcut, it does not change any property of the strongly connected component. So if it is a backward edge that you just introduce, if it is a backward edge, then you can either, you have two choices for this. You either ignore this edge, in which case you will maintain the count of r, because you can still form that many number of graphs that end at this that can reach vertex r starting at vertex 1. Or even if you decide to keep this edge, even in that case your maximum reachable vertex does not change. So this backward edge contributes nothing, and you can apply both the choices, and your like the number of graphs will increase by a factor of 2. Now suppose the edge that you are trying to add, it starts over here and ends on this left hand side. It means that one can already reach r, but you are providing it a way to reach something in between, but we know that one can already reach each of these elements already. So you are just providing a shortcut. So this also doesn't do anything, just like the backward edge. Then consider the third case, where the edge starts here and ends over here. Now even in this case, you will notice that we are adding the edges in this sorted order. It means that by the time you have reached this element, this edge will actually not be useful at all, because you can never use it, because there cannot be a connecting edge between this red line and this yellow line. Why? Because we are processing them in sorted order, and had there been a connection like so, it must have already arrived to us. So this means that this edge is also useless, just like the backward edge and just like the edge that starts over here and ends over here. So then you can conclude that the only edge that will be useful is the one that starts on the left hand side and ends on the right hand side. So this is the edge that is increasing the reach. So now all the graphs if you count the number of, before introducing this current edge, if you count the number of graphs that ended at vertex r, like this was the last reachable vertex, these many graphs will now also end at vertex, whatever this new value is, right? Whatever vertex r prime, or basically if this is x, then this is y. So you can say that if the edge this crosses the maximum vertex, then the number of graphs of this type, they will now also contribute to the number of graphs of this type. So this is the only condition that we have to handle. So now if we, so for the algorithm, you can see that all we have to do is start with a simple line graph. There are no edges added, and then maintain the count, right? So maintain the count of number of graphs that belongs to each of the classes that we define. And keep in mind that all of these equivalence classes, they need to be disjoint and exhaustive. So we have defined n equivalence classes where dp of I or dp of r means number of graphs created so far such that in all of these graphs vertex r is the last reachable vertex from vertex 1, is the last reachable vertex from node 1. So you start with this dp definition, and initially in this line graph, what will the dp values of everything be? There is only one graph where the last reachable vertex is 1, right? There is only one, and these are all zeros, right? There is no graph where you can reach vertex 2 when you have not introduced any edge so far. Now when you introduce an edge, and you introduce all the edges in sorted order, right? So you introduce all the edges starting at 1, and then starting at 2, and then starting at 3, and so on. Then you check, you try to update the dp value of all of these r's, right? So you create a new dp array. So this is the dp value of the previous iteration when you have not seen the new edge. But once you have seen the new edge, you will have to create a new dp array which denotes the refreshed values of all of these equivalence classes. So suppose these are the refreshed values, and this is the new dp array that you have to create. Then you can see that if you decide to ignore that edge altogether, then the number of graphs that you have created before you have seen the current edge, let's say 3 to 5, they will still remain the same. So that's why you will say that ndp should be initialized with dp instead of setting it to all 0, right? Because if you decide to ignore this edge completely, then you still have all the choices you have made so far, and you have created some set of graphs that end at vertex 1 or end at vertex 2, and so on. Now, but there can be some more new graphs that you might end up creating. And which are those? Those are the ones where you end up taking the vertex. And we have already discussed the case then that taking the vertex is can only improve your answer if the vertex crosses over this boundary. So all we have to check is we have to iterate over each r. Okay, iterate over each r, and then check if the edge x to y crosses that boundary. And if it does cross the boundary, then if you had dp of r, like this is the number of graphs that can reach vertex R before you have seen the current vertex, then you can create this many new graphs that can reach vertex Y after you have seen the current edge. If you take that element, then it will be like 1, 2, this is 1, this is R, and this is X, and this is Y. So then you will increment dp of Y with dp of R. So now let's look at the implementation. Yeah. So for the implementation, you can see that I have initialized dp of 0 with 1. Basically, when you have not seen any edge at all, then there is only one graph that ends at vertex 0. So this is 0 based indexing. That's why you see 0 over here and not 1. And then I read all the edges and sort them in increasing order of x. Then we iterate through all the edges, and then we already concluded that if you decide to not, you have two choices, right? You either decide to ignore the incoming edge. If you decide to ignore the incoming edge, then you will still retain the dp array, which contains the number of graphs for each classes, for each equivalence class that you have created. So you will either retain that dp array, so that's why we initialize it with dp, and the second choice is you take that edge. Now, if you decide to take that edge, then that can either be a backward edge. How do you determine if it is a backward edge? You can just check if x is greater than y. Or if it is not a backward edge and you are trying to update dp of I, right? And suppose this is 1, this is I. Then what if it is a edge that starts over here and then ends over here? Then it will not, even if you take this element into your graph, it won't really do anything, right? So an edge ending at or before I, right? So it starts here and then ends over here. And then finally an edge starting strictly after I. So even if you take this and this, then also it does not change the equivalence class of your graph, but it does increase the count by that number, right? So for example, if you had, like, let's say 3 graphs, okay, you had 3 graphs where you were able to reach I. Suppose one graph was with 1 hop to I, the second graph was with 2 hops to I, and the third graph was with 3 hops to I. Now you see that if you take anything in between, like if you add an edge like so, then still the maximum reachable vertex is I. But if you add this edge into all of these 3 configurations, then you will get new configuration, right? So that's why even if they do not change the answer, they increase the answer by the amount of the number of graphs that you already have that reach vertex I. So this is the case where they do not change the configuration after taking the vertex. Now what about the last case where they are able to change the configuration? And that can only happen when if this is I and the x to y that you are considering, that crosses the boundary. And if it crosses the boundary, then you can notice that now you can reach up till y, right? So you take all the graphs that can reach till I and their count is their count is dp of I, and you increment the number of graphs that can now reach till y. So that's why this ndp of y condition. And Then finally you swap your DP and NDP. Basically, you are refreshing the DP array that you are maintaining. So in this manner, we were able to solve the problem in. So sorting the edges will be O of m log n, assuming the m log m, assuming m is the number of edges. And then here you see that for each edge, we are processing, we are doing a for loop with n, right? So the overall time complexity become O of m into n. So that was it. Like that was the entire problem. So I just wanted to talk about the idea of how to think about these DP problems. And in case you are interested, this can also be optimized further down to m log n if you are interested. And to see how it can be optimized, it's pretty simple using some data structure. So nothing fancy there. So here you can see that for each element in a range, you want to do x plus equals to x. This is nothing but x into equals 2, right? So multiply you need a data structure that can do fast multiplication of all the elements in a range by 2, and then this is incrementing all the elements in a range by a certain constant. So you need a data structure that can multiply all elements in a range by constant and add all elements in a range, add a constant to all the elements in a range. And this can be easily done by lazy segment tree from AtCoder library. But that is not as impressive, because once you have reached this point, then it's very trivial to use data structure to optimize it further. But the goal of this video was to focus on how to approach a completely vague problem, right? Like uh, for these kind of problems, there is no predetermined way to think. So if you found this video helpful, do let me know in the YouTube comment section so that I can continue the series. And you might notice that this problem was very situational, circumstantial, in the sense that a lot of it is very dependent upon the setting of the problem, right? Like the observation that everything depends on one, and the observation that we have to sort it so that we can simplify the equivalence classes, and the observation that we can process the edges in increasing order of addition instead of doing deletions. So you might think that these are very specific to a particular problem and these might not help you in future. But if you want to grow, especially in competitive programming, these are exactly the kind of problems that will help you grow. Because sure, this exact idea of looking at a particular vertex one and then making it a central node might not appear in other problems, but all these small observations that you keep making for each problem, they eventually add up, and then when the next time a new problem comes, you'll have something to think about, the first step to take. Okay. And I know one of the first complaint that I will get on the comment section is that the video was too vague. Why did you not do a dry run and show me how things work? But I have intentionally avoided doing a dry run as such, because if you really want to improve at dynamic programming problems, you have to be comfortable with visualizing things without seeing numbers. Okay, so right now, like previously I showed you how we were able to start with a random graph, and then we saw that when we added an edge, how does the new graph looks like. So if you are not able to build this visual imagery, then you will never make good progress on dynamic programming problems, right? And how do you actually build those visual images, right? You do that not by me dry running that algorithm for you. The algorithm, you already see it on the screen, right? Just a couple of lines of code. You have to take this algorithm and start adding edges one by one, and then convince yourself how each and every graph is accounted for in just the n equivalence classes that we created. You have to do this for each dynamic programming problem that you encountered, and then if you do it enough number of times, the next time a problem appears, you will not even have to do any dry run. Most of the dynamic programming problems, you can simply look at it, visualize, assume a general case, and then expand that graph by introducing a new element, taking the choices. So dry run is not the way to go. The dry run you should do definitely, but only by yourself, by taking any example and then convincing yourself how all the cases are covered. So that's all for today, and let me know in the comment section if you have any feedback or suggestion. Thank you.